Gam Ganapataye Namaha. Let's look at chapter 1, do a revision of what we have studied so far. So, good morning, good afternoon, good evening from wherever you are watching it from, depending upon from wherever you are watching this class from. So, chapter 1, units and measurement, we began this on Monday. We'll continue this today by revising what we studied in the last class and then moving forward. So, introduction. Measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or a numerical measure accompanied by a unit. Although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities since they are interrelated with one another. The units for the fundamental or base quantities are called fundamental or base units. The units of all other physical quantities can be expressed as combinations of the base units. Such units obtained for the derived quantities are called derived units. A complete set of these units, both the base units and derived units, is known as the system of units. Now, let's take a look at it closely. So, measurement. So, measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. So, if we break down this sentence, we'll see that the sentence is talking about one action, which is measurement. So, measurement is a type of action. So, if we like simplify this sentence, we can read it by saying that measurement involves comparison with a unit. So, basically, measurement of any physical quantity. So, if we kind of skip this grammatically, then the sentence becomes this action involves comparison. So, this action is like the action of comparison with a with a certain something called unit. So measurement involves comparison with a unit. We see the definition of unit here. So comparison with a so the unit is basically described as a certain basic, arbitrarily chosen, internationally accepted reference standard. And this thing is called unit. So this sentence implicitly has the definition of unit, but it's talking about an action. So focusing on action verb here, the chapter name itself is measurement. So units and measurement. So in this sentence, both are captured, measurement and unit, and this action is described, measurement, action of measurement is described as an action of comparison. So think of this like a function. So any action can be thought of like a function, which takes something in input, does something with it, and generates something as an output. So this action takes an object, does its comparison with a unit, and gives a result. So in the next sentence, we speak about the result. So the result of this action, the result of a measurement, of a physical quantity is expressed by a number. So a number is involved whenever there is a physical quantity. Whenever there is a quantity involved, there is a number involved. So number is basically a numerical measure. You can you can call now you'd be calling this number as a measure, a numerical measure, a measure which involves number accompanied by a unit. So rightly said in the previous class, Akash, uh, 10 meter. 10 is a number, meter is a unit. So that's a good example. 100 kilometer. 100 is a number, kilometer is a unit. Good example. Although the number of physical quantities appears to be very large, number of physical quantities of anything can be infinite, from 0 to 1, 0.1, 0.7, 10,000, 10 million, anything. So there are so many different quantities possible. But to express them, what we need to do, get a number, get a unit, and you can describe that quantity to some extent. So that's what that's saying. Although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities since they are interrelated with one another. So they can be described in terms of other. For example, 2 can be described in terms of 1 plus 1. 3 can be described in terms of 2 plus 1, something like that. So by using existing things, we can describe higher or lower things by comparing to that. So that is what is being conveyed here. The units for the fundamental or base quantities are called fundamental or base units. The units of all other physical quantities can be expressed as a combination of the base units. Such units obtained for the derived quantities are called derived units. A complete set of these units, both the base units and derived units, is known as the system of units. Well understood. So now let's move on. Let's take a look at the actual paper where this information is picked from. So usually scientific research and study, they all happen in the form of papers. So about units and measurement, this is a good paper published at this location on the internet. So you see physics.nist.gov. It's a government website. CUU PDF SP330.pdf. So if you visit this website, you'll find this paper and you can read it. So this is an excerpt from that paper. So it says two classes of SI units are there. SI units are divided into two classes. दो वर्ग बना दिए जाते हैं दो हर वर्ग वर्ग इज ए ट्रांसलेशन हिंदी ट्रांसलेशन भाषांतरण ऑफ द वर्ड क्लासेस वर्गाह क्लासेस वर्गाह प्लूरल ऑफ वर्ग इज वर्गाह संस्कृत तो देर आर टू वर्ग दो वर्ग होते हैं बेस यूनिट्स एंड डिराइव्ड यूनिट्स आगे बोलते हैं फ्रॉम द साइंटिफिक पॉइंट ऑफ व्यू द डिवीजन ऑफ एसआई यूनिट्स इनटू दीज टू क्लासेस इज टू a certain extent arbitrary means कोई बिना कोई cause के taking a fresh decision making a choice and sticking with it, that's arbitrary because it is not essential to the physics of the subject. So because it is not essential, this division, this vargikaran, division, that is vargikaran. So वर्गीकरण no, classification is वर्गीकरण, division is भाग देना. तो दो भाग में जो divide किया है वो है, excuse me. Nevertheless, the CGPM, considering the advantages of a single practical worldwide system of units for international relations, for teaching, and for scientific work, decided to base the international system on a choice of seven well defined units, which by convention are regarded as dimensionally independent: the meter, the kilogram, the second, the ampere, the Kelvin, the mole, and the candela. Candela. These SI units are called base units. The second class of SI units is that of derived units. These are units that are formed as products of powers of the base units according to the algebraic relations linking the quantities concerned. The names and symbols of some units thus formed in terms of base units may be replaced by special names and symbols, which can themselves be used to form expressions and symbols for other derived units. The SI units of these two classes form a coherent set of units, where coherent is used in the specialist sense of a system whose units are mutually related by rules of multiplication and division with no numerical factor other than 1. Following CIPM recommendation 1, 1969 PV 37 30 31 and Metrologia 1976 66. The units of this coherent set of units are designated by the name SI units. It is important to emphasize that each physical quantity has only one SI unit, even if this unit can be expressed in different forms. The inverse, however, is not true. In some cases, the same SI unit can be used to express the values of several different quantities. So let's let's take a closer look and pick the things that we need and be aware that this paper is here for reference and not for memorizing. And we'll be taking a closer look just to understand that how books are made, how NCERT book is made. And then I asked you to read the preface as well. We'll talk about that, what you learned from the preface, and if possible, if you are interested, uh, we'll look at some key points mentioned there, something like that. So let's move on. So we see दो भाग में SI units दो भाग में divided हैं arbitrarily, just for ease, just like that. Divide किए तो उसमें there's just base units. 7 units are chosen as base units, and apart from that, derived units होते हैं. These units that are formed as products of powers of the base units. For example, area is meter square, power 2. Meter, which is a base unit, raised to the power of 2, meter square, is unit of area, right? Like that. These are the units that are formed as products of powers of the base units according to the algebraic relations linking the quantities concerned. So 1 kilometer equals 100 meters. 1 meter square equals 1 into 1 meter into meter. 1 meter into 1 meter. 10, 10 meter into 1 meter. Uh, that would be 10 meter square. 10 meter square, something like that. So algebraic relations form relations between derived quantities and base quantities. The names and symbols of some units thus formed in terms of base units may be, so uh, read like that. And if you are concerned about some question, you can find the answers like this yourself. Initially, you can take help, of course, but then as you are educated, this is what the ability you have. So now let's look at the next section, 1.2, the international system of units. In earlier times, scientists of different countries were using different systems of units for measurement. So scientists from different countries were using different system of units for measurement. कुछ भी नापना होता था तो अलग अलग देश के वैज्ञानिक अलग अलग यूनिट सिस्टम यूज कर रहे हैं. उसका एक एग्जांपल यहाँ दिखाता हूँ. जैसे भारत देश में यज्ञ आदि होते रहे हैं. उन यज्ञों को करने के लिए लोगों को यज्ञ कुंड बनाने होते थे. यज्ञ की वेदी बनानी होती थी. तो उसके लिए ये जो यूनिट सिस्टम है Bodhayana in the very first chapter of his Shulba Sutra. Shulba Sutra. So let's write it here. Shulba Sutra. So in Shulba Sutra, they use an angula, the finger width, is regarded as the unit of linear measure, which is to 14 grains of anu plant, Penicum meliacium, or alternatively, it's equal to 34 sesame grains put together with their broad sides together. We have here a summary of these units. So, like this, many different countries, all different countries have different unit systems. These are provided in advanced notes as part of the repository. You can read them here. Have links also, and there are some other resources you can study. And some relation to computer science. In computer science, we also use units. For time, we use units. So, like that, it has extensions. And this is the appendix which we talked about. So, it's also here. And these are all derived units. And yeah, some other files that were used for making the video. So, let's move on. So here, as we see, there are different systems of units used by different countries, but then some kind of standardization was needed. Why it was needed? Let's take a look at this. I've mentioned there was a incident that happened, right? So one space mission to Mars crashed because of this uh, conversion of one country measurement from one country uh, system to another country system. So let's take a read. So, Mars Climate Orbiter incident in 1999, the spacecraft launched by NASA was lost because of a mismatch between metric and imperial units. Lockheed Martin, which built the spacecraft, provided acceleration data in pound force seconds, imperial units, while NASA's Jet Propulsion Laboratory (JPL) navigation team expected Newton seconds, metric units. This error caused the orbiter to enter Mars's atmosphere at too low an altitude, about 57 kilometer, instead of the planned 226 kilometer, resulting in its disintegration due to atmospheric friction. The $125 million mission failure highlighted the critical need for standardized units in space missions. So that's what we see. So there's this funny uh, jibe at it, at a yeah, because it was a machine, a loss of money, loss of a country's dignity, but or like it not let's not take it that far. So okay, enough of this. So we see that we needed a standardized system, right? So this is this. Now let's move on. Page 3. So we see hmm, so this is some units retained for general use, though outside SI. So there are some units which are retained for general use, which are these: minute, 60 second, the name, symbol, value in SI unit. So there are values mentioned in SI unit here, and these are units retained for general use. So minute, hour, day, year, degree, liter, ton, carat, bar, curie, Roentgen. I do not know how to read that, but I would say it Roentgen. Quintal, barn, R hectare standard atmospheric pressure. So note that when mole is used, the element, okay, so in this previous page, we see there are tables. So here, okay, so we missed this part. So we already did this in the previous class, and there are some terminologies which are not described here, and they are mentioned like for the first time in this page. So we'll discuss them later. And this is the seven base units and their definitions. And this was part of the homework, so we can discuss what were the set of questions that you might have. And we saw that this is not supposed to be memorized, so that finishes the revision. And we also discussed some notes that we did not discuss in the previous class. So that was one additional value that we had in this recap. Let's move on to the chapter 1, page 3. So in this we see that note that when mole is used, mole is also a fundamental or base unit basically. The elementary entities must be specified. So whenever you are using mole unit को जब use करोगे तो किस elementary entity की बात की जा रही है वो बताना होगा. The elementary entities must be specified. So as we saw, mole is basically these many elementary entities. 6.02214,076 into 10 to the power 23 elementary entities. So what are these elementary entities that must be specified if you are using mole? That is the idea here. So we see these entities may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. So you can have groups of such particles also, uh, and there could be mole of those groups. So you can make complex objects out of elementary objects, and then make that as an entity, and use mole to describe how many of those entities. So multi-universe or multiverse, those kind of things can be described with more by specifying each unit or each elementary entity is basically a universe in that context. We employ units for some physical quantities that can be derived from these seven base quantities. We also already saw that, and we already finished till here. So appendix is done. Let's move on to significant figures. So if you have I kind of jumped over it, but the hope is that you already read this paragraph. And even if you have any questions or doubts, you can speak about that in the next opportunity that you get. So, significant figures. As discussed above, every measurement involves errors. Thus, the result of measurement should be, as discussed above, every measurement involves errors. Thus, the result of measurement should be reported in a way that indicates the precision of measurement. So, the result of measurement should be reported. So, this reporting action is now happening. So, measurement action has happened. Now, the reporting of the result is happening in a way that indicates the precision of measurement. Normally, the reported result of measurement is a number that includes all digits in the number that are known reliably, plus the first digit that is uncertain, right? The reliable digits plus the first uncertain digit are known as significant digits or significant figures. So, in the result of measurement, there's a number, and all but one number are certain, and the final last not number basically. All but one digits are certain and one digit is uncertain. So together, this all the certain digits plus one uncertain digit, this whole number of digits is called significant digits or significant figures. So all these digits Uh, a certain plus one uncertain. All these digits together are called significant digits or significant figures. So if we say the period of oscillation of a simple pendulum is like this, is 1.62 second. Let's say the period of oscillation is 1.62 second. We'll know about what a period of oscillation is. But for now, I'll tell you that if a pendulum starts from here, goes like this, comes back here, that's one time period for that pendulum. So if it is 1.62 second, the digits 1 and 6 are reliable and certain. So 1.6 is reliably known. 2 is uncertain, while the digit 2 is uncertain. Thus, the measured value has three significant figures. 1, 2, 3. The length of an object reported after measurement to be 287.5 cm has four significant figures 1, 2, 3, 4. Simple so far. The digits 287 are certain while the digit 7 is uncertain. Clearly, reporting the result of measurement that includes more digits than the significant digits is superfluous, and also misleading since it would give a wrong idea about the precision of measurement. So, after the uncertain digit, if you add more digits, it's not going to make a lot of sense because even the measurement to that extent is uncertain already. So, let's limit it to one uncertain digit and not go beyond that. The rules for determining the number of significant figures. The rules for determining the number of significant figures can be understood from the following examples. Significant figures indicate, as already mentioned, the precision of measurement, which depends on the least count of the measuring instrument. So, precision is accuracy. Uh, how closely you could calculate or measure, how accurately you could measure. That's precision of measurement, which depends on the least count of the measuring instrument. So, the measuring instrument is limited to counting to a certain extent. It cannot go beyond that. So, that is also signified here. So, there's an example, this vernier caliper and all. There are some precision measuring instruments that are called vernier calipers. So they also have limitations, physical limitations. So a choice of change of different units does not change the number of significant digits or figures in a measurement. So changing the units does not change the number of significant digits in a measurement, in a measure. So the result of a measurement is a measure, and in that measure, we have a numerical figure and a unit. So the numerical figure has significant figures or some digits which are significant. So, and a unit. So, number of digits that are significant is independent of the unit. So, significant digits unit से independent होते हैं. For example, the length 2.308 cm has four significant figures. 1, 2, 3, 4. These are the four digits which are significant digits or significant figures. But in different units, the same value can be written as 0.02308 meter, that was centimeter, and this one is meter, or 23.08 millimeter, or 23080 micrometer. This is called mu meter or micrometer. All these numbers have the same number of significant figures, digits 2308, namely 4. This shows that the location of decimal point is of no consequence in determining the number of significant figures. So the location of decimal point is of no consequence in determining the number of significant figures. Uh, बिंदु बिंदु कहाँ पे लगी है, that will not, वो नहीं तय करेगा कि कितने significant digits और significant figures हैं measure में. The example gives the following rules. All the non-zero digits are significant. Clear. All the zero between two non-zero digits are significant, no matter where the decimal point is, if at all. If the number is less than 1, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. So this is a more complex sentence. Let's break it down. If the number is less than 1, so number is less than 1, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. So right of the decimal point but to the left of the first non-zero, so these two numbers are not significant. The underlined zeros are not significant. So, so yeah, if it is less than 1, then of course the the number that would be on the left of the point would be 0, unless it is written in a scientific notation. So that will come later. Sorry for bringing that up. But anyways, so this statement, if the number is less than 1, then the zeros on the right of the decimal point, but to the left of the first non-zero digit are not significant. So these zeros are not significant. Even this is not significant. Uh, the underlined zeros are not significant. The terminal or trailing zeros in a number without a decimal point are not significant. So if the number does not have a decimal point in it, then the trailing zeros, these are called trailing zeros. These are not significant. So 123 meter, 123 meter equals 12300 centimeter equals 123,000 millimeter has three significant figures, the trailing zeros being not significant. However, you can also see the next observation. The trailing zeros in a number with a decimal point are significant. So if you bring in a decimal point, then things change. After that, the trailing zeros after a non decimal, the trailing zeros in a number with a decimal point are significant. So these numbers are significant. These have four significant figures. So this is some point of confusion. So in this, there's no decimal point. So these three zeros are not significant. But this number has a decimal point. In that case, these zeros become significant. So in this case, if you bring in a decimal point, then things change. So if you bring in a decimal point right here, then we'll have 1, 2, 3, 4, 5, 6 significant figures if you bring a decimal point here. So this is confusing. That's what they are trying to tell here. There can be some confusion regarding the trailing zeros. Suppose a length is reported to be 4.700 meter. It is evident that the zeros here are meant to convey the precision of measurement and are therefore significant. So these zeros need not be mentioned, but they are mentioning it. Therefore, these must be counted as significant digits. If these are not, it would be superfluous to write them explicitly. The reported measurement would have been simply 4.7 meter. Now, suppose we change units, then 4.700 meter becomes 470.0 centimeter, 470 mm, or 0.004700 kilometer. Since the last number has trailing zeros in a number with no decimal, we would conclude erroneously from observation above that the number has two significant figures, while in fact it has four significant figures, and a mere change of units cannot change the number of significant figures. So here in this case, By changing the unit, it might appear that we can ignore these two zeros because trailing zeros uh, are not significant figures unless it is a decimal point. So, let's observe it further closely by moving forward, and then if we have to come back, we can come back here. So in this case, it can be erroneously concluded that it has just two significant figures. That's what they're saying. To remove such ambiguities in determining the number of significant figures, the best way is to report every measurement in scientific notation in the power of 10. In this notation, every number is expressed as a multiplied by 10 raised to the power of b, where a is a number between 1 and 10, and b is any positive or negative exponent or power of 10. In order to get an approximate idea of the number, we may round off the number a to 1 for a smaller than equal to 5, and 10 and to 10 for a greater than 5 and smaller than equal to 10. Then the number can be expressed approximately as 10 to the power b, in which the exponent or power b of 10 is called order of magnitude of the physical quantity. So somehow, if you have a number, you can always represent it in a way that this A is a number between 1 and 10, and B is any positive or negative integer. So in that case, A would be either 1 to 5, including 5, or 5 to 10, including 10 but not including 5. So we can take it as a 1 or a 10 by approximating it. In that way, every number can be represented in this form. So A will be absorbed in this, in which A का मान इसके अंदर 10 के अंदर चला जाएगा B घट या बढ़ जाएगा, in which the exponent or power B of 10 is called order of magnitude of the physical quantity. So B, the exponent of that number, would be called the order of magnitude of that physical quantity. Let's see. When only an estimate is required, the quantity is of the order of 10 to the power B. For example, the diameter of Earth, 1.28 into 10 to the power 7 meter, is of the order of 10 to the power 7 meter with the order of magnitude 7. So, order of magnitude is 7. The diameter of hydrogen atom, 1.06 multiplied by 10 raised to the power of minus 10 meter, is of the order of 10 to the power minus 10 meter with the order of magnitude minus 10. Thus, the diameter of Earth is 17 orders of magnitude larger than the hydrogen atom. See, 10 here and 7 here. So, yeah, it makes sense. It is often customary to write the decimal after the first digit. Now, the confusion mentioned in A above disappears. So, it is customary to write the decimal after the first digit. So, you have the first digit, put the decimal there. So, now the confusion goes away. Now, this number has four significant figures because it has a decimal in it. So we'll count these two. And then it can be turned into 4.700 into 10 to the power 2, 10 to the power 2 centimeter. Still keeping the number same, changing the power of 10. And that way we'll keep the significant number of significant digits consistent. The power of 10 is irrelevant to the determination of significant figures if the number is written in scientific notation. However, all zeros appearing in the base number in the scientific notation are significant. So, except for 10 raised to the power aspect, the number aspect, all the digits in that would be significant figures. Thus, in the scientific notation, no confusion arises about the trailing zeros in the base number A. They are always significant. Fourth, the scientific notation is ideal for reporting measurement. Good. But if this is not adopted, we use the rules adopted in the preceding example. So it's recommended to use scientific notation for reporting your measurement, but if you don't adopt that for some reason, we use the rules adopted in the preceding examples. So we'll remember those rules because probably definitely there will be exercises we'll be dealing with those. For a number greater than 1 without any decimal, the trailing zeros are not significant. A number has to be greater than 1. It should not have any decimal point mentioned. The trailing zeros are not significant. For a number with a decimal, the trailing zeros are significant. Simple. The digit 0 conventionally put on the left of a decimal for a number less than 1, like 0.1250, is never significant. However, the zeros at the end of such number are significant in a measurement. Cool. The multiplying or dividing factors, which are neither rounded numbers nor numbers representing measured values, are exact and have infinite number of significant digits. The multiplying or dividing factors, which are neither rounded numbers nor numbers representing measured values, are exact and have infinite number of significant digits. This is out of uh, common general understanding. So, infinite number of significant digits, although it might have just less number of digits. But if the number is, let's say, it has decimal, yeah, then in that case, okay. So it's crucial to note. For example, in r equals d by 2 or s equals 2 pi r, the factor 2 is an exact number and it can be written as 2.0, 2.00 like that. So it can have infinite number of significant figures because this is accurate, exact. It's not a measurement. That's why. Okay, so let's take a break here. So the factor 2 is an exact number and it can be written as 2.0, 2.00, or 2.0000. Sometimes while speaking, people might call 0 as O, and that's okay, that's fine. It's understood in the context and nobody minds it. Similarly, in t equals small t by n is an exact number. So for exact number, the number of significant digits is infinite. Rules for arithmetic operations with significant figures. So now let's take a look at this, and with this, we'll close this today's class. The rules for arithmetic operations with significant figures. The result of a calculation involving approximate measured values of quantities, that is, values with a limited number of significant figures, must reflect the uncertainties in the original measured values. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it was obtained. Thus, if mass of an object is measured to be, say, 4.237 gram, four significant figures, and its volume is measured to be 2.51 centimeter cube, then its density by mere arithmetic division is 1.68804780,876 gram per centimeter cube up to 11 decimal places. It would be clearly absurd and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based have much less precision. The following rules for arithmetic operations with significant figures ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured values. In multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figures. Good rule. So now let's give this as an exercise. So you have to explain section 1.3.1 to me and explain how the examples are, like completely explained section 1.3.1. I hope that is okay. So let's take this as an assignment. So please, assignment 3 is please explain the section 1.3.1 and let me write it in a way that does justice to sanity. So, uh, okay, so this should be good. So with this, let's close today's class. Bring your questions, and the idea is to have interactive sessions. So the way I am able to provide a video asynchronously, feel free to ask me questions about how you'd be able to provide such a response or a question in the form of a video. We can talk more about this on our Discord channel.